Okay, let me have a look. We will do two things now. Okay, and they're both involved in, we do a live coding here. Let me stop this poll. Okay, right. Two things I want to achieve. First of all, we kind of start where Stefano left off with this, this issue of the parameter space that we look at for a certain measurement, right? Articulation rate cannot be negative. So if we specify priors that go into the negative space, that's all kind of odd. So I want to pick you up here, and we want to talk a little bit about model criticism, right? We want to check ourselves whether the model that we use is appropriate for our measurement, and our whether the model assumptions really are appropriate for what we want to look at, right? And there's a really neat way to do that, at least like a rough, quick and dirty way to do that in with BRMS. So let me share my screen with you. And here I have, let me also get the chat going. Here I have the code from earlier. We built this simple model, if you remember, right? In which we predicted articulation rate based on attitude, and we specified some priors, right? Weakly informative priors. We ran the model, right? And I can post this into chat again, just in case you want to rerun it. I've ran it already, just for now, so I can show you something in particular. So as Stefano already said, there are no negative values for articulation rate. And that is true for other measurements such as F0 or duration, for example, right? And that has consequences for our outcome measurement. And we can see that using a very interesting function, the PP check function. It's a posterior predictive check, okay? And it takes the argument of the model you want to look at, okay? And there's an additional argument you can use and that I use right now to make the point a little clearer, okay? So if we run this, a plot will open. I will make that plot large enough so you can see what's going on here. There are two things, two kind of types of elements. There's this dark blue line, that's our data, right? And then there is, and on the x-axis you see right now, that's articulation rate. So we're on that scale. On the light blue lines, and there are 100 in this case, these are simulated samples from our posterior, right? These are basically simulated distributions from our posterior based on the model assumptions we have. And you might see something going on here, right? There is the light blue lines. They are very symmetric, right? There's a normal distribution that is here assumed because we use the Gaussian link function. But our data is slightly skewed, right? It's kind of tilting to the left and has a long right tail. This is very common for measurements that are bounded by 0. We find it for duration, we find it for F0, we find that for response times often when we do perception experiments, right? So what the model assumes and what the data look like is not quite in line with each other, right? And by this posterior predictive check, we can notice these divergences and we can react to it because we want to obviously run a model as appropriate for the data, and thus gives us a more accurate rendering of plausible values that we can work with, okay? And you probably have heard that before, and this is not part of the course, but in these cases, for example, response times, I'm sure you've heard it, when these measurements are bounded by one side, that means variation is restricted on one side, but not on the other, and that's why you get this skewed distribution with the heavy right tail. And so what you do is you log transform. I'm sure you've heard that before. You log transform your measurement, right? What we will do now, we will use a different family, a different linking function for our likelihood, okay? And that will be the log normal likelihood. So we will not go into a logistic family at the moment, but everything that applies in the frequentist realm when it comes to logistic regression, how to specify logistic regressions applies here as well. So it's not a big leap. We'll talk about log normal for now. So let me first just simply plot articulation rate in log space, okay? for us to get an idea what's going on. I just put that up here so we have it. Right. And let's have a look how that actually looks like. So why do I do that? Well, I want to have a rough idea if I want to use a log normal likelihood function. I want to have a rough idea where the values are, so I can specify priors, right? So we can see here the mean is somewhere around 2 in log space, right? And ranges from 0.2 to 2.6. So that is helpful, right? So we want to now specify priors in log space because we use a log normal family. Right? So this is similar to when you, for example, use a generalized linear model and you use a logistic regression, for example, then you need to specify your priors in log odd space, right? So you need to keep that in mind. So here you realize again, you require a good understanding of generalized linear models to wield these tools appropriately. So, sorry, I have scrolled down and I was totally the wrong place here. Right, there we go. I'm very sorry that I'm confusing here right now. So let's actually specify some priors, and we call them my prior log. Okay, and we specify for this simple model again 3 parameters, right? And I will just use, I think Stefano had that on his slides. I will just use the ones that he specified. That is, the intercept is going to be 0, centered on 0 with a standard deviation of 2. Okay. That is for class intercept. We have our prior for our beta coefficient, right? And that will be specified as 0.25 standard deviation, class. And that was the coefficient for attitude pole. And finally, we have our sigma, our residual error, right? And that was defined in his slides, I think, as 0.1. How do I arrive at these numbers? Oh yeah, thank you. How do I arrive at these numbers? Well, I look at the data, right, to get a rough idea of where data are, like what's the measurement realm in which we're talking here. Usually we have good domain knowledge. When we log transform, we might have a little less crisp intuition, but when we use measurements in their respective parameter space like F0 and duration, we usually have a good idea what are plausible values, and Stefano talked about it quite a bit, right? So this was C, right? So these are the priors. And then we run this model again, right? And this time, the only difference will be that we use, obviously, these new priors, right? My prior log with the log, with the priors defined in log space. And I change the family to log normal. And if you're interested in what kind of families BRMS offers, what kind of linking function, you can just look at the help file of the function BRM. So that is what we do, right? And if I didn't make a typo here, that should do the trick. I will post this into the chat again. I think I was reasonably close to, or maybe not, a little bit more conservative than what Stefano posted. Right, so while this is compiling, there's a question. Am I correct that when we really have no knowledge, we can just check the data itself to estimate the priors? Yes, you can to some extent guess the ballpark if you really have no idea by looking at the data. Usually this should happen in advance, right? But often when we estimate parameters, we are more in an exploratory mindset. And if we really don't have a good understanding of the underlying quantitative system, then obviously visual inspection and descriptive statistics help a lot to understand these models, right? So instead of looking at the model results now, because they will be in log space and they will be a little bit less intuitive for us to interpret. I just wanted to show you the posterior predictive check for this model now, okay? And we will again plot several more samples. By default, it just simulates 10 lines, but I think with 100, it's much better and easier to see. Right. This looks much better than before. So there's an interesting point that Stefan is making. There's always some amount of knowledge that we should have. For example, we know that in F0 in humans, we wouldn't expect values necessarily above 1,000 hertz, right? And when we talk about syllables per second, we probably do not expect 50 syllables per second. That's probably out of the range of things that we would measure in normal communication, right? So there's always some knowledge we have, and it obviously helps to use descriptive exploration to understand the quantitative system a little better. So this is one way to kind of evaluate, is my fit in the right ballpark, or did I, violate an assumption? Is my scale entirely off? And this way we can have a rough idea of what is going on.
Timo, can you share the last code they're asking in the chat? The last lines, I guess it's... the
PEP check?
Yeah, I assume.
Again, when you look at the exercise file for the session, it's 08. There's a detailed walkthrough through a more complicated example that walks you through this entire process. So you don't have to stress right now. You can review that later. And there I have much more prose that kind of describes what's going on, what the reasoning process is. What we did so far seem not really relevant for our day-to-day analysis, right? We've only dealt with super simple models. We basically predict the mean based on one predictor, on an attitude condition here, right? And we ignore super important aspects of the data set, and several of you have already pointed that out. The data is hierarchical in nature, as our data often is, right? There are multiple speakers that produce several data points across the two conditions. And if we do not account for this dependency, we violate an important assumption of linear models. It has nothing to do with Bayesian, has something to do with the underlying mathematical assumptions of a linear model. And I bet this is kind of old news to most of you. The field used mixed effects models now for the last 10 years, I think. But if you still feel a little shaky on that front, we highly recommend reading up on this issue of dependency and then the independence assumption. Again, Bodo Winter's book is a good departure point for that. What is new now, though, is running these beasts with BRMS, right? So we want to account for the fact that different speakers have different articulation rates. So some speakers speak faster, some slower. And we want to account for the fact that different speakers might have a different effect of attitude on their articulation rate, as you can see here when you look at the different lines, right? Some show a negative slope, some show a positive slope, some show like a level slope, right? So we will do that now together. Okay. So let me just open a new text file here for you. Forget this picture here, right? And forget all this shenanigans here. And we will now dive into a linear mixed effects model. And you can imagine this is a little more involved because suddenly we have more parameters. And now we have to actually understand what parameters is. So we just had this model in front of us. I would just type it down here, right? There was articulation rate predicted by attitude, right? Plus, and you're familiar with this syntax, a random intercept for subjects. So we allow them to differ in terms of their articulation rate. And we add, in this case, a by subject slope for the factor attitude, right? So that's what we want to do. So how do we go about this? Well, we already know how to go about this, right? So first of all, we want to get prior for this model, right? So this is the formula without an A, without an R at the end, and the data set is polite, right? So if we do that, you already, that's the moment, right? So here we get already the parameters that should be specified as priors. And you see this table is already quite a lot richer than the ones before. But let's identify first what we know already, right? We know already the parameter for the intercept, right? That's our reference level. We know already the residual error, sigma. And we know already the beta coefficient. And you remember there are two different ones here. There's one that is specific for the coefficient attitude pole. And then there is a general one that has no specification for a coefficient. That's all old news. Now let me take this out for you. Don't worry about this. This is a correlation coefficient that estimates the correlation between random effect levels, right? And I will tell you a rule of thumb that you can apply always when you have to specify the prior for this correlation class. It's pretty simple. Let's not talk about this. This is complicated stuff. What we need to talk about a little bit more is this part here, right? This is also all new parameters. And here you see they have the class SD. They are parameters for variance components. And we have several new things here. We have, for example, a group level specified, right? And the group level, let me, that's a little off. Did I do something? Oh, I'm sorry. That's total crap. I don't see the chat. No one has corrected me. Yeah, attitude. That's obviously, you know, it's a long day. So obviously we want to have a bi-subject slope for attitude. So let's run this again. This was a little odd, right? But everything that I said was so far true. The only thing that was a little messed up was this part. Okay, here we are again, right? So we want the standard deviation for, like, how much do different subjects vary their random intercept, and how much do they vary in the two different conditions, attitude informal and attitude polite, right? So we have the intercept, and we have the two random slopes, the two random effects for their individual attitude levels, right? And you get, again, you get these parameters, which are basically hyperparameters. They are general parameters that specify all variance components for all groups if you don't specify anything specific. And if you specify this one, you will specify all variance components for this group subject without specifying which coefficients you're referring to, right? So that's mind-blowing, is a little bit much, but we will just specify those things. We know conceptually what they do, so we will specify them. So let's do this. We will call them my mind-blowing priors, okay? And we will specify all of them together. So first of all, we start with the stuff we know. Prior, and maybe someone can help me out and post the priors I specified earlier in here. So we had a normal prior for, and I need to log normal ones, what we just did. Maybe Steph, you can.
Yeah, just a second, sorry. I need to get the slide.
I think that
it was normal 0.3 for the intercept and normal 0.1 for B.
For B coefficient, we always want to specify as specific as possible in this case, right? So we have that. Yep. Then we have sigma.
Yeah, that's
we had Cushy.
Yes, 0.1.
0.1.
Yeah. Sorry, no. Yes, 0.1. Yep.
Yeah. That was our sigma, right? So these three we had earlier. That's exactly the same thing, right? And now come the random effects. Oops. On top. That's these 4 parameters that we need to specify. Let's first kind of knock out the one that that I told you you shouldn't worry about. Okay, so that is let me just open something up here. That is the correlation coefficient, right? So we will specify that by a very specific prior distribution, the LKJ, Lewandowski-Korowicka-Joe prior. And we're, by the expert, we are recommended to use the scale factor 2, okay? And that covers our correlation parameters. Let's not worry about them too much at the moment. Okay, so knocked out. Next one is our the random intercept variation. So how much speakers actually vary across each other in terms of how fast or how slow they are speaking, right? And here we'll use, again, a normal prior. And I will go with something similar to our residual error, 0.1 Cauchy, okay? So we will specify that. That is the class SD with the coefficient intercept. So I'm looking at this line down here, right? And the group subject. Check. Right? Next, we are now specifying this one here, right? And we will use very boring priors. Sorry, I wanted to use Cauchy in all of these cases, right? So we basically use the same prior for all these variance components because it covers most of the ground that we want to cover. It will cover most of possible values for the variation, how much speakers will actually vary in these particular, for these particular variance components, okay? So in this case, we specify the coefficient. Where were we? Here, right? So the coefficient is attitude inf. And again, this is group subject. You can have different grouping variables in here. For example, if you have a crossed random effects model, like when you have different speakers produce different words, right? And different words are produced multiple times. Then you might have another random effect grouping for words or for sentences, for example. And finally, we have, oops. We have the final part of the random effect slope specification, right? So here we are. We have the 3 parameters we had before, and we have 4 parameters that are all relevant to the random effect structure, right? So let's see whether that actually works out. Let's actually make that a little smaller here. Right. So we have specified our priors, and now we will actually run our model. We call it the mind-blowing model. Okay. And that is this specification here. Right, and I will make it a little easier to read like this. We have to add our prior. That's the my mind-blowing priors. You should usually use shorter variable names, but this one's fun. And we have to specify the family, which should be log normal, right? So let's see where that works out. As you can, it compiled, so that's a good sign. As you can imagine, we specified a bunch of more like different parameters here as prior, so the overall sampling procedure will be slower, right? This is a small data set. There's not a lot of data points, so it's still rather quick, and it's still rather a simple model. You know what you've ran in the past, right? I have run much more complicated stuff with interactions, three-way interactions and multiple grouping factors, etc. Right? This is still a rather easy model, but it captures all of the relevant aspects of a linear mixed effects model that we need here to understand how to run these things. The compilation takes always 30 seconds, maybe a minute. And now you can see the sampling is much slower than what it was before, right? When we ran it before. Still pretty quick, right? Now, before I finish, and I really need to get done here, we have a quick look at the output. So what you see here in the output is what you've seen before, right? You get the population level effects that still, these are the predictors you're interested in, right? These are the things you're estimating that are probably relevant for your research question, for your research hypothesis. This part of the table here is new. These are the parameter, the descriptions of the posteriors for the parameters that are related to the group level effects. You have the random intercept, basically. You have an estimation for the variance across speakers in the attitude informal condition, in the attitude polite condition, and you get a correlation coefficient as well. The standard deviations here, the variance components, they're all positive. They can't be negative, right? So they are, as you can see here, they are somewhere around 0.01 to 0.1. The correlation coefficients, they can always be between -1 and 1. So here you see you get an estimate that is kind of around 0 with a credible interval between -0.8 and 0.8. Right? But these things, they can be informative, but we won't go into detail here. Usually it's not what you look at. What you usually look at is this one, right? So this hasn't changed. And overall, this is very similar to what you do in the frequentist realm when you use learnB4, similar information you get, right? The thing that we added here, and we'll post this in chat again. Or is it already? Oh, it's already posted. Great. That is the new part, the prior specification, right? And this is, it's very involved, and I will get back to that in a bit. Again, so if you have loaded the learnB4SS package, then you can open exercise. You know what I love? I don't know where we figured it out. If you put in a number that's not in here, it tells you that this doesn't exist, and you should choose the ones that exist. It's just, I love it. So basically you want to pick number 8. That's the one that we just did. And it opens an R Markdown with 2 parts. At line 33, there's a walkthrough, what I just did with a little bit more complications. I added another predictor as well. And then in line 365, I think, no, yep, no, 365. There's an exercise that you can do where I ask you to apply the knowledge from the workthrough to another part of the data set. So if you walk through this, I think you have a good idea of what the necessary steps are in such an analysis. And I hope that's helpful.